Today we are going to discuss about engineering physics PH 8151 Unit 3 Thermal Physics Part B questions. So it is coming under Regulation 2017. It is common for all the branches of the engineering in Anna University. So Unit 3 Thermal Physics. The following topics are there: transfer of heat energy, thermal expansion of solid and liquids, expansion joints, bimetallic strips, thermal conduction, convection and radiation, heat conduction in solids, thermal conductivity, Forbes and least disk method, theory and experiment, conduction through compound media, series and parallel. So thermal insulation and applications, heat exchanger, refrigerator, oven and solar water heater. Here we are going to study briefly about the flow of heat through compound media. So flow of heat through compound media having the two portion. The first one is a metal bar in series. So a two metal bar is placed in a series position. Second one is here. Second main part is here two metal bars in parallel position. So two position how the heat is flowing, that only we are going to discuss here. So first one metal bars in series position. So here two object is there, two object A and B. The two object thickness value x1 and x2. The two object A object B object both are touched or connected position temperature value theta. A starting temperature value theta 1, final temperature theta, and B starting temperature theta and final temperature is here theta 2. So the A side is a hot end, B side is a cold end. Let us consider a compound media of two different materials A and B with thermal conduction K1 and K2. So here K1, K2 is a thermal conductivities of A and B, and x1, x2 is a thickness of A and B material. So the temperature of the outer phase of the A and B are theta 1 and theta 2. So the temperature of the surface in contact is theta. So when the steady state is reached, so when the temperature is reached in a steady state, so that time the amount of heat flowing per second through every layer is same. So here amount of heat we are considered as a capital Q. So the amount of heat energy flowing through the material A per second Q is equal to K1A theta 1 minus theta by x1. Equation number 1. So amount of heat energy flowing through the material B per second Q is equal to K2A theta 1 minus theta 2 divided by x2. Equation number 2. In steady state condition, equation 1 is equal to equation 2. So K1A theta 1 minus theta divided by x1 is equal to K2A theta minus theta 2 divided by x2 is equal to equation number 3. So rearranging the equation number 3, then we can cancel the A, and that denominator will come to the numerator position when it changes to the other side of. So x2 will come to left side, x1 will go to right side. So k1 theta 1 minus theta into x2 is equal to k2 theta minus theta 2 into x1, equation number 4. From equation number 4, a cancel, then we can get the equation number 6. K1, so x2 is multiplying inside in left side, in right side x1 is multiplying inside. The x, what are the values are outside, that value we are going to multiply inside. So left side k1 x2 is here outside, we are going to multiply inside in each numbers, each value. Right side k2 x1 is outside, so we are going to multiply inside the each value. So k1 x2 theta 1 minus k1 x2 theta is equal to k2 x1 theta minus k2 x1 theta 2, equation number 6. Next, in equation number 6, the minus value I am going to move opposite side. So left side equation minus value I am going to move right side. The right side equation minus value I am going to move to left side. Then it will become positive. then equation value will be changed. The k1 x2 theta 1 plus k2 x1 theta 2 is equal to k2 x1 theta plus k1 x2 theta. That is equation number 7. Here the right side, theta is a common, then we can take it outside. So theta open bracket k2 x1 plus k1 x2, that is equation number 8. Then we can find out the theta value. Then right side, the bracket values are will go to left side, means it will come to the denominator position. So theta is equal to k1 theta 1 x2 plus k2 theta 2 x1 by k2 x1 plus k1 x2, that is equation number 9. So this is the expression for interface temperature of the two composite bars in series. From equation 1, we can substitute the theta value. Then Q is equal to K1A by X1 into theta 1 minus theta. Instead of theta, we are going to substitute here I substitute the theta value. Then equation number 10 came. In equation number 10, I am going to take the common LCM. So here LCM is a K2 X1 plus K1 X2 is LCM. So then equation number 11 came. Next equation number 11, that minus is common for bracket value. Then minus I am going to move inside. So if you move inside, so then already inside the bracket everything is plus, then everything will be changing to minus form in equation number 12. So in equation number 12, two values are plus or minus value, but both values are same, but the symbol is different. Then it will be cancelled. Then we can get the equation number 13. Q is equal to K1 A divided by x1 into k2 x1 theta 1 minus k2 x1 theta 2 divided by k2 x1 plus k1 x2, that is equation number 13. Equation number 13 also inside x1 is common for only the denominator, then we can take it outside. So x1 also cancel in 14th equation. Then we can get the equation number 15. Q is equal to k1 k2 also common take it outside. So k1 k2 a into theta 1 minus theta 2 divided by k2 x1 plus k1 x2, that is equation number 15. So in equation number 15, that the k1 k2 value, just I am changing the position, but if you change the position also, the value it won't be changed. That is the main thing. Then equation number 16 we can get. So q is equal to a into theta 1 minus theta 2 divided by k2 x1 plus k1 x2 divided by k1 k2. Then this the, the down position, we can split the value because k1 k2 is common for 2. Then we can split, means we can cancel, we can simplify the equation. So q is equal to a into theta 1 minus theta 2 divided by k2 x1 divided by k1 k2 plus k1 x2 divided by k1 k2. So the first value k2 is there, cancel. Second value k1 is there, cancel. Then we can get the equation number 18. Q is equal to a into theta 1 minus theta 2 divided by x1 by k1 plus x2 by k2. So here Q is the amount of heat energy flowing through the compound wall of the two material. In general, for any number of bars, the amount of heat conduction per second is given by, so generally we can write, so Q is equal to a into theta 1 minus theta 2 divided by summation of x by k. So equation number 18 is correct, and the equation number 19 is a general equation for this condition, metal bars in series condition. So thank you, all the best for your future. Thank you.